Welcome everyone. Yeah, we're going to be talking about CMake Superbuilds and converting them to Spack stacks, why you might want to do that, and some of the background behind why each of these things exist. Quick introduction, probably most of you saw this yesterday. I'm the Spack on Windows guy. I work at Kitware. I do a bunch of other things as well, including a lot of CMake language work. Bit of a roadmap, we'll cover CMake Superbuilds. We'll talk about converting a CMake Superbuild to a Spack stack, why you might want to do that, and then kind of a dive into the process of how you might go about that in the general case. So kind of backing out a little bit, why are we all here, right? Why is C++ dependency management so hard? And I think basically we're all here because we didn't like a lot of the answers to that question that we got. And we wanted to improve on them. So we attempted to, and that's Spack, right? And C++, Fortran, et cetera, package management is very hard, right? There's a lot of considerations that make rolling your own approach to this, essentially infeasible. That's not news to anyone here. In the beginning, there were bash scripts, right? And then you find some version, fetch it, build it, you have it, there you go, you can use it, install it. It codifies a process for fetching and installing dependencies. It's less manual than a hand fetch, it's automatable, but it's still incredibly manual, it's painstaking, it's all of the issues with rolling your own or doing your dependency management by hand, except you can deploy it in CI really quickly. Then we created system package managers, your deb packages, your RPMs, homebrew. It's way more automated. You don't have to do your own dependency resolution. You don't have to update your own packages. You don't have to know how to build anything, or at least not that much. It's also very inflexible, unoptimized. You have minimal control, Windows Who. And this all might sound very familiar to a certain tutorial intro that you might have all heard before. There's a reason for that. I also noted homebrew has a Spack package, which is kind of funny. And then from kind of system package managers, those aren't flexible enough, so how do we solve that? CMake Superbuilds, and this is something I see a lot. I think once you have the CMake tool, it's like that quote, once you have a hammer, everything kind of looks like a nail. Once you have a CMake system, the go-to is kind of just hammer CMake at the problem, and usually it works out. And that's kind of, to a degree, that works, it scales, and that's how we have CMake Superbuilds. What are CMake Superbuilds? Here's an example of a bunch of them. These are basically independent CMake projects that are separate from your whatever core repository you're trying to build. So let's say ParaView, you have a ParaView Superbuild. It's not in the ParaView repository, it's not in the ParaView CMake code, it's an independent project. It is written in CMake language. It's typically external project based, a little bit of example of a code snippet adding VTK as an external project there to the right. You basically, the same way you would for a system package manager or a hand-rolled bash script. You vendor all your dependencies, you coordinate the acquisition, the configuration, the construction, basically, and the installation of the dependencies. You basically manage their entire lifecycle via CMake. The reason we use external project is because that makes it incredibly easy to do so. CMake actually has a ton of internal infrastructure to make all of this very straightforward and simple. And all you really need to know how to do is how to, where to get this dependency, how to build it, and then that's pretty much it. And especially if it's another CMake project, right, you get all that fine package benefits, and everything kind of just works together seamlessly, particularly if you exist fairly consistently within the CMake ecosystem. But external project add can run, auto tools, it can run make files, it can run nmake, it can run all of these other sub-build systems. It can run, I don't know if you've got a pure Ninja file, but it can run that, right? And then you can either roll your own CMake fine package or integrate it into your existing CMake workflow. And you also don't have to use CMake to consume CMake Superbuilds, right? You can just use the nice infrastructure of external project add, throw everything in an install tree, and let auto tools and whatever else you're using do its existing dependency resolution logic. Really, it's not that much different. You just ignore the CMake config file. And like I said, it integrates into your existing workflow pretty well. It also requires manually specifying dependency ordering. You have to do manual conflict resolution. If this version of HDF5 conflicts with this version of netcdf, conflicts with every version of zlib for some reason. You have to figure all that on your own. Every time there's a new release, you have to go, if you want it, you have to go get it yourself, figure out how to build it, any changes, any new conflicts, etc. And you still have to know how to build every single sub-project of your project. So if you want to build ParaView, you got to know how to build like 30 different projects. Well, at least if you are attempting to maintain the ParaView Superbuild. The nice part is you can maybe shell that out to 30 different developers, and you each have to master one, but that is still a fair amount of on-team manual effort. So why do we use CMake Superbuilds? They basically allow us to have monolithic builds without monolithic repos, or just ad nauseum Git submodules. They're a bit flexible. They can be from source or binary. You can do unified builds, separate builds. You have fairly flexible configuration over subprojects, right? You have arbitrary control over their flags, their build arguments, et cetera. You have full control over dependency management, their builds, what order they're built in. You can parallelize them a little bit, not inside. CMake doesn't have parallelism in and of itself, but if you're using Ninja to drive these, and Ninja's, the sub-projects are also using Ninja, that's fairly parallel. It also uses existing CMake infrastructure, right? If we have the CMake hammer, we're going to see a bunch of CMake nails. And it's fairly controllable. And yeah, they definitely could work. They mostly do work, right? For ParaView, for VTK, for CMB, for a bunch of medical software, for ITK. But I think there's probably a better way. Like I said, the CMake Superbuilds are flexible. They're exactly what you need, exactly the way you want it, exactly the way you asked for it most of the time. They're highly configurable. You have atomic control. They're modular and easily extensible. But like I said, they're manual. They're a pain to maintain. And they're certainly a pain to update and modify. Like I said, manual dependency resolution and conflict resolution. And you've got to manage combinatorial explosion by hand, right? If you want 30 different variations of a package, and those all have a bunch of patches and changing dependencies, you have to manage it. You have to have CMake options for all of that. You have to have different arguments. You have to have a ton of forking logic in your CMake. You have to have maybe a ton of different CMake files. It's hard to manage. And like I said, yeah, dependency resolution is DIY. You have to make sure everything builds in the right order and tell CMake about it. And if you forget, then you might have a bunch of broken builds that are potentially hard to debug. I think you can probably all see where I'm going with this, because all of the issues here seem oddly solvable by a project we're all familiar with. And that would be Spack, right? So this is an example of a CMake Superbuild. Fletch is actually the first task Kitware ever gave me. They asked me to build Fletch on my laptop. I spent like 2 days banging my head against it. I was on a Windows laptop, because of course I'm the Windows guy. And then I think Bill told me like 2 days later, oh, it doesn't build on Windows. It never has, or it hasn't in like 3 years. And like 4 days later, I had it building on Linux. But building a Superbuild should not take a new developer 4 days, right? And I was fresh out of college, so maybe I wasn't the most efficient at building large-scale C++ ecosystems on my own, but should still be somewhat more consistent than that. And then I'm not bashing CMake Superbuilds by any way, shape, or form. They have their place. They're very useful, and they solve a lot of problems for a lot of folks. And if you're already using CMake, it's a natural conclusion. And Fletch is incredibly complicated. It builds tons of vision and AI components that are incredibly hard to install. But we can do better, and we can Spack it. So we'll look at, I'm going to use Fletch as a motivating example, and we'll look at kind of pulling Fletch apart and converting it into a Spack stack as opposed to a Fletch CMake Superbuild. If you're curious about the name Fletch and the arrows, there's a project that supports called Quiver. So Fletch, fletching is the arrow, fletching on the arrows of Quiver. Anyway, so why do we do this? Or why would you want to convert a CMake Superbuild into a Spack stack, right? You have your basic package manager benefits, right? You don't have to maintain the packages. I'm the Spack CMake package maintainer along with Massimiliano. I assure you, we're pretty good at that. So you don't need to maintain your CMake package, right? Ryan is a very, very good steward of the ParaView package. I can't really name any, Adam Stewart is a fantastic maintainer of the bajillion packages he happens to maintain, right? All of the Spack package maintainers are pretty good at their jobs. We typically know what we're doing, and if we don't, we know who to ask usually. In addition to that, you have all the other package manager benefits of Spack does the fetching for you, Spack does the staging for you, Spack does the installation for you, it does the environmental setup, it does all of these really nice things that you don't have to deal with. Basically, it abstracts a large portion of the, infrastructure and kind of ops portion of dealing with CMake Superbuilds or dealing with dependencies in general. And different from CMake Superbuilds, you have access to binary caches, right? There's, if you build a Superbuild, it's on that machine. CMake doesn't, CMake is not a package manager, right? It doesn't have an inherent ABI model. It doesn't have, it doesn't know which things work on which platforms because, it knows where it built, but you'd have to infrastruct all of that in CMake language to get it to work. You get Spack's combinatorial management. You have more options for your users, right? When you make a CMake Superbuild, you say, I want Qt, I want zlib, I want geotiff, I want OpenBLAS, I want OpenCV. And then you've got to choose which versions of their dependencies you use, and so on down the chain all the way to the version of GCC you're selecting. And unless you want to go through every single possible combination of those things yourself, you typically just statically pick a couple of common use cases and go with them, and then implement those in your CMake Superbuild, and they kind of just work, right? It's static, it's consistent, it's stable, but it's super inflexible, and your users have basically no choice. And realistically, do you care which version of zlib HDF5 is building against? Odds are you do not, right? It's way down the stack, and you're focused. And you typically, if you're installing HDF5, you're typically focused far higher than HDF5 itself anyway. I'm just picking HDF5 out of thin air as an example, right? Let's see, OpenCV, you're doing, if you're installing OpenCV, you don't care about, its various dependencies. You're building something probably far on top, like some complex vision algorithm far on top of OpenCV. So it allows, basically converting to a Spack stack allows all of those, kind of minutia decisions that you would normally be forced to make in a CMake Superbuild just be abstracted to the Spack solver, and you can focus on the packages you actually care about. Basically, it's far less maintenance, far more flexibility, and more focused on development and less focused on being a human package manager, essentially. So let's look at actually converting a CMake Superbuild to a Spack stack. First, let's pull apart a Superbuild. So the anatomy, like I said, it's very external project-based. You have your, and then within those external projects, you might see some very familiar concepts, right? You have your versions, you have your variants, you have fetching, you have installing, you have dependency coordination, right? You have CMake has add dependency. You have some URLs, you have some options, you have some patches, you have all the things that we see kind of every day in Spack packages. And then to the right-hand side of the slide here, you can see the ad nauseum list of all of the CMake language files that are hundreds of lines long that define all of this, which could be reduced to about 6 or 7 lines of a declarative Spack file, and then maybe some a CMake args method. We also have some common config options, right? We have from the root level of the Superbuild, we can enable versions, we can enable packages, we can enable variants at a really high level. Again, this has to be kind of duplicated inside the CMake build system, right? You've got to specify your options for the user, and then you have to actually go through and process all of that logic behind the scenes in your actual CMake language code, and then have a bunch of branching if statements and all this complicated logic that Spack can somewhat, to a degree, abstract for you quite a bit. We also, like I said, we have a ton of patches in Superbuilds, right? This is a third of the patch files. They did not fit on the screen, that are in Fletch, right? Very similar to Spack. It's a direct one-to-one translation. There's kind of nothing special here, just Superbuild patches into Spack patches. Superbuilds also have a ton of scripting. Typically, they're done to support various things, kind of the same way Spack's various in your package recipe ad hoc methods are. Maybe they do some platform-specific logic. Maybe there's some helpers for a common task that you need to solve for a given package. Whatever extra special sauce you need to build this particular piece of software. And then just looking at the overall size of a Superbuild, this was 453 files, the Fletch is, and it's, 7,000 lines of CMake code, or 5,000 lines of CMake code. It's long. It's a big CMake Superbuild system. ParaViews is significantly larger than this. Not significantly, maybe 20% larger. Either way, it's a lot, right? It's all this is a very small subset of the Fletch CMake Superbuild. This is it in Spack as a Spack YAML. It's the whole thing. This produces basically, at least on my machine, a one-to-one mapping of everything Fletch is capable of, minus, I ripped a couple versions out because we don't care. So just kind of a proof of concept of this is how much easier it can be if you choose to migrate to a Spack environment. So how do we actually start this process, right? So the first thing we need to do when we are constructing a Spack environment and to create a Spack stack, right, is what do we add, right? We need something to populate this stack. And it's not everything. You should not be one-to-one mapping every single external project add call in your CMake Superbuilds to a root node in your Spack stack. You want a minimal set of roots. This allows maximal flexibility and maximal reuse. Right, Spack solver is pretty smart. So let it do as much of its genius as it can, and save yourself the pain and difficulty of over-specifying dependencies that maybe you don't care about. Like I said, the zlib example earlier. You're not that interested in probably the base level dependencies in your stack. So you don't need to constrain them the way you would inside the CMake Superbuild. That being said, you do still need to meet the needs of the project. So if you do need to constrain them, then you do need to add them as a root spec, or specify them as a dependency of a spec, the way you define it when you add it to the environment. But mostly, what you should add as root nodes to your stack is the find package calls in the consuming project. So maybe that's a bunch of consuming projects, so the number of specs in your stack can grow quite a bit. But typically, you want to change from your perspective, looking at kind of how to construct this, from looking at everything in the world that I need to build to what do my users actually need and actually care about. And it allows you to kind of focus more on getting things correct for them, as less on the minutia and details of building 1,000 things. You want to look at supported compilers, of course. You want to look at per platform environments, right? If you want different things on Mac OS versus Windows versus Linux versus some cluster, you want to, all of those considerations exist in the CMake Superbuild, and they would be translated pretty directly to your Spack stack configuration. And basically the way I go about this is, I let the AI invent the title there, but basically I specify everything that I need, identify all my root nodes, all my find package calls, the versions, the variants, and find package maybe can't specify every single variant in the world. It's not exactly a one-to-one mapping of everything you can do in CMake. So at that point, you do kind of need to look at what options the Superbuild configures, and map those to variants. Maybe you need to add a package, or maybe you need to add a variant, make your own package repository, etc. However you choose to achieve modeling the requisite CMake build options into your spec, stack, or package. And then basically you concretize, you inspect the results of the concretization, you determine, maybe it concretized to some insane version that doesn't work for your package. You go, like, oh, you missed a constraint, go back, constrain it, reconcretize until the spec, the output of spec or spec concretize looks vaguely correct. From there, you install, assuming everything installs correctly and nothing breaks. You test, you build your actual core piece of software you care about. You presumably build it successfully. If you can't, kind of go back to step one, look at your specifications. Did you overspecify, underspecify? Do you need more things in your stack? Do you need fewer things? Do you need to be a little bit tighter about your compiler restriction? Do you need to have more platform specifics? Do you need to add an external? Stuff like that. And then once you have your project built and testing, and the tests are passing, you kind of inspect the results of the ecosystem, and maybe there are things you overconstrained and you can take out that don't affect the results of this. Maybe you missed a feature. Maybe there's a plugin that you didn't, that's not part of your build, but it's part of your runtime, and your tests choked on that. Basically, it's an iterative cycle, right? It's not a direct one-shot from CMake Superbuild to completely perfectly spec'd out Spack stack, right? It's a cyclic iterative process, kind of just like general software development is, right? There's the build, develop, build, test, deploy cycle, except maybe cut off deploy for this because you don't want to push up a broken Spack stack. So, like I said, CMake Superbuild gives direct atomic control over dependencies. It is very important to consider, do you actually need all of those things? And will the default Spack variants meet that use case? If the default Spack variants don't meet your use case, you might need to add some. You might need to make, and if they're proprietary, not upstreamable, you might need to make your own Spack repository. But basically, without getting into the weeds of the implementation details of a particular deployment, it is important to consider for pretty much every package in your CMake Superbuild whether or not you need it, and whether or not you need all of, whether or not Spack natively supports all of the various options and configurations and requirements that you have for the CMake Superbuild. So getting into the actual process of converting it, the software that you want to build isn't already in Spack, map your patches to your patches, your versions to your versions, your variants to your variants, et cetera, so on. It's fairly straightforward and analogous concepts. Typically, I've found most CMake scripts fit well into the build or install methods for a package, or just maybe a helper method in the package recipe. That's worked fairly well. And then once you hit maybe a bit of a sticking point is, let's say your CMake Superbuild has a bunch of options, right? You can build, it says, VTK version is an option, and you might say 9.5, 9.3, et cetera. You might want a couple versions of foo. You might want some different versions of different supported GCCs. CMake builds one configuration at a time, right? You could iteratively reconfigure CMake with different options and not blow away the build tree and have all these things. but that doesn't really map nicely to install, and it's somewhat difficult. So CMake builds one option at a time, but Spack's environments can't be configured dynamically on the command line, and they don't need to be, right? Spack's environment should not be dictating what your users consume. It just dictates what is available to your users. Or doesn't, sorry, I shouldn't say dictates. It specifies what is available to your users. So it's again, a kind of a change in perspective on how we're actually viewing this process from being kind of strictly specifying things in CMake and providing this kind of more open and robust environment from the Spack perspective that allows your users to kind of select what they want at a given iteration of configure time for their project versus they having this strict static set of options that they aren't able to step outside of. And that is kind of the nice part of Spack, right? I alluded to this a little bit earlier. Spack is super flexible, right? If your user wants to build with this or needs this highly specified version of OpenCV, it may not be in your super build, it might not be maintainable there, but Spack might have it. And if your stack doesn't care about it, there's no reason a user can't constrain to use that particular version. So my recommendation is use matrices in your environments, right? Build a whole bunch of things and let your users pick what they actually want to be using via find package, via environment subsets, via things like that. And again, this is maybe more of a user-facing decision, but like I said, CMake is really configurable. Your CMake Superbuild users are typically used to being able to specify, like, I want all these -d options on the command line that result in this kind of static, deterministic, specific configuration. And these are, maybe you want to just toggle a variant on and off. Again, that doesn't necessarily exist from the Spack environment command line, but you can do it with environment includes. Maybe you can have an optional include for Mac, for Windows, for Linux. I'm sure we all have some interesting per machine include schemes. That concept scales fairly well to the concept of converting CMake Superbuilds into Spack stacks. And you can also map more high-level configuration targets, right? You have an include based on the existence of an environment variable, so maybe you want like a super GPU-y environment this time, and you don't want to install all of it. You could set an environment flag, and that would kind of map to the existing CMake configuration. This might be a little less Spacky than we're used to, but from the CMake user perspective, and those who are used to CMake Superbuilds, this provides kind of a nicer transition from what they're used to the more Spack idiom of things. Like I said, it mirrors the CMake configuration a little bit more directly. It's a little bit easier for users to adopt to. And then when we're constructing the stack, a few more things to consider. We need to identify whether we want unified or separate specs. Which specs do we want as which, especially with spec groups coming out, the ability to, that's going to be really, really useful for converting these. The ability to group certain specs into discrete concretization units would be very helpful, especially if a bunch of things rely on genuinely conflicting versions of things, right? The CMake Superbuild doesn't care if you build 4 versions of GDAL that all hate each other and can't be loaded into the same process image, or varying packages that don't play well together. Because if you never intend on loading them into the same image, it doesn't matter, right? Especially this is true with like plugins and things like that. So most things can be unified, some cannot. The CMake Superbuild doesn't model this. So it is something you will have to consider going into your Spack stack construction. Identifying unifying specifications, compilers, optimizations, etc. Basically, if you can reuse, if you can unify, great, but make sure you're doing that correctly and building exactly what you expect to be. Identify divergences, usually it's per compiler or per platform, but it'll depend on your project. And if you're building Python bindings, strongly recommend you unify, particularly your version of Python. I cannot tell you how many times I've built CMake Superbuild projects or just interacted with projects that built both C++ via CMake and pulled things in by pip, and boom, I have 1,000 versions of the same shared library in my environment, and things are just kind of falling apart. So, strongly recommend if you're using Python bindings or building them, you unify as much as humanly possible just to make sure that that final Python wheel that you're going to deploy has like a consistent version and won't conflict with other things in your environment. Like I said, populate the environment with as many versions, variants, etc. as are potentially needed. Allow the consuming project to select it. It should be dictated by the consumer, not the provider. Let CMake do its find package calls. Let you kind of constrain what's available in the environment. And then build caching, right? So one of the nice things about a CMake Superbuild is you build it once, maybe on a CI machine, maybe in a Docker image, and it's just always there. You don't have to rebuild it. unless you're updating it, which is the reason we're doing this. But in terms of a build cache perspective, it has a 100% hit rate all of the time, guaranteed. You will never waste a single second in CI either crashing because you don't have a dependency, or or building a dependency. So typically developers don't like it when that changes and they're starting to waste CI minutes building LLVM, or their CIs are flaky because you've set build cache only and the build cache is missing. So for CI, for the general case, if you have the space, go crazy. Put it. Obviously we'd all like to have petabytes of free cloud storage, but if you have the space, put whatever you can into the build cache. Put it in there. A high hit rate is good for your users. It's good for CI. It's good for everybody. But balance that with data costs, availability. Obviously you can't put everything in the universe in the build cache as much as we want to in CI for Spack upstream. But do what you can. Ensure the highest possible hit rate for your developers, and also encourage them and provide documentation for them to set up local build caches if they've got a machine that has maybe a niche architecture, or they just want some very specific things. A lot of this is also providing documentation to your users, so tell them, or provide scripting or tooling to help them set up build caches a little easier. But for CI, always use log files. Just build for a specific CI machine or Docker image. Typically, your CI environments are very consistent, right? You shouldn't be surprised by the environment your jobs are running in CI typically. So that means we have something concrete to rely on, and we can use log files. We can produce a concrete Spack environment, use that log file, use those specs to populate the build cache, so that in your CI machines you have consistent hit rate. Like I said, superbuilds are always static, so we want to kind of mimic that behavior, and we definitely don't want to waste CI minutes building random stuff, right? If you happen to miss a Rust build cache hit, you're building LLVM. That takes a while and is space intensive at times. And then in terms of shipping log file around, bake it into your Docker image, bake it into your CI machine, kind of just grab it as part of your CI. However you want, maybe host it in a different repository, in a different cloud, however you host that log file somewhere, but keep it somewhere consistent. And then for actually constructing the build cache itself, see Ryan's talk. I actually pulled out a bunch of slides because Ryan did them. We probably should have coordinated a little bit. But yeah, I would just see Ryan's talk for how to construct a proper stack, because it's the exact same process. There is no real difference. The common stacks talk is the proper way to go about this. But the short version is start broad, populate your kind of base build cache with a lot of generic things, and narrow as you go if you need GPU things, if you need things for a specific AI stack, et cetera. And also maybe have some additional stacks additional environment files that kind of pull from each other to further constrain and specify what you actually need for a given deployment, development context, et cetera. Basically, start broad, verify you have what you need at a high level, narrow, repeat that process. And yeah, that's all I have for converting a CMake Superbuild to a Spack stack. If you have any questions.
Any questions for John?
Oh, oops. Nice.
Test. Hi, thank you so much for the presentation. I'm one of these people that uses Superbuilds for quick development and still has a spec package. Are you recommending I should not have a Superbuild anymore at the end and just do everything in a proper spec stack?
Wait, sorry, I missed the first part of that one.
In my development cycles, I still mix both, right? I have most of my external dependencies as a spec package or any kind of package manager that works, but I still do a small Superbuild just locally for the closest dependencies I have, just because it's so convenient. Is that something you would recommend against, or says this is a way to go?
I guess I'm not recommending against using superbuilds. This was, I guess, supposed to be kind of a trade-off between the two. I think for most use cases, a Spack environment works far better. It's less maintenance. It's more scalable. That being said, if you need a 15-minute, even a quick 15-minute prototype, a Spack environment's typically, especially if it's already a Spack package, it's already a little bit faster. Especially if you're used to creating Spack packages, it's a pretty quick process if you just need to stub out some basic things. That being said, if you already have a bunch of CMake architecture, if you need a quick prototype, CMake Superbuilds can definitely be fine. But for long-term development maintenance practices, I would definitely recommend a Spack stack, personally.